Hello everybody, online lecture number 16. The last time we spoke about the stability of reactive intermediates, and we learned that there are so-called inductive effects. So inductive effects are based on differences in the electronegativity in the atoms of a molecule. So if you, for instance, have a positively charged carbon, a carbocation, and it is connected through sigma bonds to these residual groups. Now, when these residual groups are more electropositive than the carbon, the positively charged carbon, then the carbon withdraws electron density from these residual groups. We call this the positive inductive effect or plus I effect. This leads to stabilization of this carbocation so that it does not immediately continue to react to form a product, for instance. So it has a longer lifetime due to this positive inductive effect. This is the negative inductive effect, minus E. Now this is the opposite. These residual groups now, they are more electronegative and they can stabilize carbanions. So this carbon, which has an additional electron now, is stable because these electronegative fluorine groups, they pull the electron density towards them and therefore results in a lower energy of this carbanion that stabilizes the molecule. So then next, after inductive effect, we spoke about hyperconjugation. Hyperconjugation is usually a stabilization mechanism that works together with the inductive effect. So here is a carbocation again. It has an empty p orbital, and adjacent to it is this methyl group. The methyl group is sp3 hybridized, so it has 4 bonds, and one of those sp3 orbitals is in the right orientation to overlap with the empty p orbital of the carbocation, and this causes the electrons here in this sp3 orbital to become more delocalized. They are pulled towards the empty p orbital, and that stabilizes this carbocation again. So that helps the positive inductive effect here, for instance. So in this lecture, we're going to talk about so-called mesomeric effects. So they are a little more sophisticated, so I'll spend a little more time on them. Let's get into it. So mesomeric effects, they are different from inductive effects, because inductive effects, they are based on pushing or pulling electrons in sigma bonds, right? But mesomeric effect, on the other hand, they involve the delocalization of electrons through pi bonds. This is a famous system that has pi bonds, benzene. So benzene has 6 carbons, and between the carbons there are alternating double bonds. Now experiments show that the distance between each of these carbons, between a carbon pair, is always the same. You would be expecting there to be different distances, because in this drawing here there is a pi bond here and there's no pi bond there. So where there's a pi bond, you would have a different distance to where there's no pi bond. But again, experiments show that all the distances are the same, and that is a hint for the system being delocalized. That means the pi bonds, they can be here or also there at the same time, and this is called delocalization. So the pi bonds are equally distributed over the entire molecule and shared between all the carbons. So you can now use the Schrödinger equation to calculate the wave function for benzene. And remember, the wave function can have a positive and a negative sign. And here is the outcome of this computer simulation. Here the region that is light gray, the surface plot, is a negative wave function, and the dark plot here, the surface, is a positive wave function. So you can see now this is the 1 pi, the lowest energy pi orbital that forms in this system, and the electron density is distributed over the entire molecule, right? It's not in between only 2 carbons, but it's spread over the entire space. This is delocalization. But you have here 6 carbons that form this pi network, and for 6 carbons you also form 6 molecular orbitals. So here is the second one, this is the 2 pi, that's a little higher in energy than the 1 pi. Here there is indeed not such a high level of delocalization, but now there's more concentration of the electron density between 2 carbons here and 2 over there. And the next molecular orbital that you get is the 3 pi, which has also electron density concentrated in other regions of the molecule. So there's also a 4 pi and a 5 and a 6 pi, but those are not occupied by electrons. These here are the bonding electron molecular orbitals, and the others 4 pi, 5 pi, 6 pi are the anti-bonding molecular orbitals. So let's look at a more simple example of the delocalization. So instead of benzene, I look now with you at butadiene. So you see butadiene has 4 carbons, and between 2 pairs of the carbons there are also these pi bonds. So what we can do with the description of the bonding in this system is now we split it into a sigma framework and a pi network. So first the sigma framework. These carbons, they are sp2 hybridized, right? That means they have 3 sp2 orbitals. Here's one that connects to a hydrogen, here's one that connects to another hydrogen, and the third sp2 hybrid orbital connects to the adjacent carbon. And the pi system is then composed of these out-of-plane p orbitals of the carbons. So here they are drawn, and they are still drawn as atomic orbitals, right? So just these lobes with positive and negative wave function. But in reality, these are overlapping, just how you saw in the computer simulation for benzene. But for simplicity, it is drawn as atomic orbitals. So these 4 atomic p orbitals, right? They have now the same energy level, right? They are degenerate, we say. But if the molecule forms now, if they begin to interact with each other to form this pi molecular orbital system, then the 4 atomic orbitals, they split into molecular orbitals, and the molecular orbitals have different energy levels. And the 1 pi molecular orbital is the lowest energy, the 2 pi is also lower in energy than the atomic orbitals, but the 3 pi, for instance, is higher. And that means 3 pi and 4 pi, they are anti-bonding molecular orbitals, and 2 pi and 1 pi are bonding molecular orbitals. So here's a schematic of the 1 pi molecular orbital, and has the lowest energy because all the lobes with positive wave function are on one side of the molecule, and all the lobes with negative wave function are on the other side. So there is so-called constructive interference between all of them, and that leads to the lowest energy of the system. So the 2 pi orbital, on the other hand, has also constructive interference here on the 2 halves, but in the middle there is destructive interference, and this causes there to be a nodal plane in the molecule, and that increases the energy a little bit because of the destructive interference. So for the 3 pi, there are 2 nodal planes, so more destructive interference, and for the 4 pi, even 3 nodal planes, and that causes there to be higher energies. So think about how many electrons are now in this pi system. So each p orbital has 1 electron, right, that is ready to bond with an adjacent p orbital. And I now distribute the 4 electrons from the p orbitals into the 2 bonding molecules. And the message from this is now only the bonding orbitals are filled, not the anti-bonding, and therefore the whole bonding by this pi system leads to a lowering of the energy of the system, and therefore a stable configuration, right? This is now a stable energy configuration because the pi system has a lower energy than the individual p orbitals. So even more simple, now looking at propene, instead of butadiene, propene. So propene, it does not have such a pi bonding network. It has only 1 pi bond here, right? Because the carbon on this side is an sp3 hybridized carbon. So it has 4 sp3 orbitals and no empty p orbitals, so no pi bond. However, if you use a very strong base, then you can pull away one of the hydrogens from here, a proton I mean, and that leaves behind the electron from this hydrogen, causing the carbon to become negatively charged, and you get the so-called Allyl Anion. So now the Allyl Anion has again an empty, it has a p orbital that's filled with with 2 electrons. So now the system here, the Allyl Anion, has 3 p orbitals, and they again split now into a pi network by forming these molecular orbitals. So 1 pi molecular orbital, 2 pi molecular orbital, and 3 pi molecular orbital. And again, for the 1 pi, the wave function is having only constructive interference, but for the 2 pi, you have a nodal plane with destructive interference, and for the 3 pi, even more destructive interference. So now remember how many electrons are there in the system that are available for the pi network. So there's 1 in this carbon, that is in the empty p orbital, or in the p orbital filled with 1 electron. There's 1 in this carbon, and there are 2 in this carbon because 1 has been stolen from the hydrogen after the base took the hydrogen away. So we can distribute these 4 electrons now into the 1 pi and 2 pi, and overall this leads to a lowering of the energy of the system because the anti-bonding is not filled. The 2 pi is neither anti nor bonding molecular orbital, it's somewhere in between, but overall the lowering of the energy from the 1 pi stabilizes the system. So you see again an example of how delocalization of the electrons in a pi network leads energetically to stabilization of the molecule. So now going back to this definition of mesomeric effects, here is again a drawing of the Allyl Anion, this time hand drawn, and here we have the negative charge on the end carbon, the additional electron, and over here is this double bond system with the pi and the sigma bond, and we call this a negative mesomeric group, a -m group. So -m groups, they stabilize carb anions, and here's why. The negative charge from the end carbon can jump over here, and the electrons from the pi orbital can jump to the carbon at the end, and that shifts the pi bond from over here to there, and now you have this -m group having accepted a pair of electrons, right? So the end carbon here is now negatively charged, and this arrow that has 2 heads, one on the left and one on the right, that means that these 2 configurations are in so-called resonance. Resonance means that both of them are present at the same time, just how in the benzene molecule the pi bonds are spread over the entire molecule. Here we have this delocalization, and that results in a so-called resonance hybrid. So instead of drawing the pi bonds on one pair of carbons or on the other, we can draw it also with this dashed line, and that indicates that it is delocalized and that we have a partial negative charge at the end carbons, and overall charge of this Allyl Anion is negative. So negative mesomeric groups, they stabilize carb anions by accepting a pair of electrons, right? So here's another example of a negative mesomeric group. This oxygen here connected via a double bond. So what can happen here? The negative charge of the end carbon can again jump to in between these 2 carbons, and then the electrons from the pi orbital here, they can jump to the oxygen to form a lone pair, and as a result you get a negatively charged oxygen and a double bond down here. And in this case you have actually a more stable configuration for the charged oxygen because it is more electronegative. So the electron density is held more tightly to the oxygen, but nevertheless these two are in resonance. So there's again a resonance hybrid, and this lowers the energy of the molecule and it stabilizes the carb anion. It's called the negative mesomeric effect. So I show you computer simulations now. Here is again a negative mesomeric group, such an oxygen that has these pi bonds also, and now the pi bond from the in between the two carbons can jump over there, and the electrons from the pi bonds here can jump to the oxygen, forming a lone pair, causing the oxygen to be negatively charged. But again, these two are now in resonance, right? So here is the computer simulation of the 1 pi orbital that has formed from this pi network that is in this system, in this molecule. And you see here, this is the end carbon here. Here is the in-between carbons, and here is another in-between carbon. And at the end, behind here, is the oxygen. And you see for the 1 pi orbital, the electron density is more concentrated here in the back where the oxygen is located because of its higher electronegativity. So this is not a symmetric molecular orbital now, but because of the electronegativity of the oxygen, the electron density is more concentrated at the oxygen. And therefore, the hybrids, the resonance hybrid here is more stable. The 2 pi orbital has more electron density actually between the carbons. The 3 pi and the 4 pi, you see, with the higher in energy we go, again, the more nodal planes we have in between the orbitals. One last example for a negative mesomeric group. What you see here is a carboxylic acid, right? So in the acid-base equilibrium lecture, we learned this is a weak acid. It can deprotonate. So now we have deprotonated version, and there's a negative charge on the oxygen. But again, this can form a resonance hybrid because the negative charge can be either on this oxygen or on the one above, right? So, and these two now are in resonance. So now we look at the energy levels that lead to the formation of this resonance pi network. So first, there is an orbital that's involved, which is the pi orbital between the carbon and the oxygen, right? So carbon has one atomic orbital, a p orbital, and oxygen has a p orbital, and these two p orbitals combine to form a pi orbital. But they form, since two orbitals, atomic orbitals, form two molecular orbitals, we also have a pi antibonding molecular orbital that forms from combination of two atomic p orbitals, right? So this is always the rule. Two atomic orbitals form two molecular orbitals. So now we know there's one electron in the carbon p orbital, one electron in the oxygen p orbital. Now these two electrons combine to go into the lower energy pi orbital, right? So the other orbital that's involved in the formation of this pi network is the lone pair on the oxygen, right? That involves a p orbital that is filled with an electron originally from the oxygen and an additional electron from the hydrogen that has jumped off. So these two electrons are now in this 2p orbital of the oxygen, and the these two orbitals here, they can now combine to form two, again, molecular orbitals. But since the entire system involves three orbitals, right, the bonding and anti-bonding from the CO bond and the p orbital from the oxygen, we also have to form, again, three molecular orbitals. The 1 pi, the 2 pi, and the 3 pi. So we can now distribute the electrons. 2 go into the 1 pi, the lowest orbital, and 2 go into the 2 pi. And there are none left for the 3 pi. So overall, the energy is lowered, especially because the 1 pi orbital has such a low energy, right? And this is the negative mesomeric effect. The energy has been lowered, and this stabilizes now the negative charge on the oxygen based on this delocalization of the electrons. So the computer simulation, solving the Schrödinger equation, getting the wave function, shows now how the 1 pi orbital looks like, the one with the lowest energy. The electron density is distributed over the entire molecule. So the oxygens and the carbons, they all share this electron now, the pair of electrons. So this is stabilizing this molecular orbital system. And the 2 pi orbital, it has only electron density on the 2 oxygens and none at the carbon. And the 3 pi, or we don't have to worry about it so much because it's anyway not filled with any electrons at the moment. So these 2 orbitals lead to a lowering of the energy, and this is the negative mesomeric effect. So here's a comparison. A carboxylic acid, we've learned, it reacts with a base, water in this case, to form a deprotonated carboxylic acid. And this is now stabilized by the negative mesomeric effect based on the delocalization of the electrons in this pi bonding network. On the other hand, an alcohol, that is not a weak acid, right? Alcohols, they don't deprotonate. And you know the reason why? Because there's no negative mesomeric effect for alcohols. So the alcohols, I show it in the equation here, they can deprotonate, but extremely little. So they have a very, very low equilibrium constant. The equilibrium constant for the carboxylic acid is significantly higher. And this is because of the negative mesomeric effect, because of the stabilization by resonance by a delocalized pi network. Okay, I think your head is probably already smoking. But this is it for now. In the next lecture, we will continue with the mesomeric effect. See you!